would like to welcome to the stage our next presenter, Michael Holberg, presenting 5G transport network requirements and architectures. Michael is a distinguished systems engineer at Extreme Networks. This is his second time presenting at NANOG, and we're very happy to have him speaking to us. Michael, there he is.
All right, good afternoon. So everything is moving to the cloud, and basically your network is no exception in that sense. So one key thing I kind of believe, based on the previous presentation, is that 5G is the first cloud-native mobile technology generation. And looking at that, 5G is much more than just radio and the core. It's things like management, orchestration, software-defined networking. It is things like policy-driven AI and ML, and transport. So I'm going to spend the next 30 minutes kind of talking through the same topic as the previous presentation. I think for people who actually are not that into the 5G part, the transport part, I think it was a quite deep dive, the previous presentation by Igor. So I'm going to touch on quite a lot of the same things that Igor touched on, but I'm going to try to actually, simplify a bit things and pinpoint, this more from a network point of view. And with that said, let's move into kind of going through these things. So how I want to start this is, as said, more like building up or building up the picture for you here. I think Igor touched on the previous generations, being the 2G, 3G, LTE compared to 5G. But I wanna start this with truly compare those two, because there is a huge difference in the transport network requirements, as I guess that many of you guys kind of realized based on the previous presentation. So if you look at 4G, 4G is one key service. It's one shared transport network. It is best effort, and it's basically, latency is not that critical. Then you go into things like the point-to-point backhaul. So for 4G, you are actually using layer 2 point-to-point backhaul. Carrier Ethernet is completely fine for that. And then you have a single RAN architecture basically for that one. So looking at 5G, first of all, 5G have a service-driven architecture, which basically means that you have 4 things predefined. RAN is one thing, 5G core is the second thing, the hyperscalers is the third thing, and the fourth thing is transport. And obviously, as I said, I'm going to touch on the transport part, more on the network side of it. In addition to that one, on the previous presentation, you heard about network slicing, isolation. How would you be able to actually have the same network providing multiple different isolated slices for different services? So you truly go into different, slicing mechanisms, slicing types. You have a service slice or the service instance layer. You have your resource instance layer, and then you have your network instance layer. So as you can see, it's starting to build up the picture here of 5G being far more complex than the previous generations. So then you go into, as said, hand in hand with network slicing, you have things like multiple different applications, consumer-based, it could be enterprise-based things. So you start to look at traffic classes. Could be best effort traffic, could be, things like the enhanced mobile broadband, which basically bandwidth is the key requirement for that one. Or it could be low latency applications, where you probably have heard of the kind of, so many times used use case for that one, which is autonomous cars, which basically means that it's truly latency sensitive. And that's kind of referred to as the URLLC, use case. Now, with that, you start to look at actually having traffic within an area or region being CU to CU communication. And then, as we heard in the previous presentation, you start to actually move the routing boundary more out towards the edge, which basically means that instead of with 4G and the previous generations where you actually had point-to-point backhaul, now you start to move into, a dynamic multi-destination connectivity type for the xHaul part here. Then you actually have multiple RAN architectures. In the previous presentation, it was not really covered, the different RAN architectures that you have there. And then you start to virtualize things. So you virtualize your core, and then you have your control plane and user plane is virtualized. In the previous presentation, Igor was touching on the CU and the DU part. The CU part being basically the control plane and the user plane, while the DU part is actually then the latency sensitive radio functions. And as said, if you start to virtualize those, that means that you actually move them out from the specific purpose-built hardware. So this to kind of set the stage here for what I'm going to basically talk about here the next 20 minutes or so. So looking at the different network architectures. So O-RAN was kind of discussed in the previous presentation as well. O-RAN is not an architecture per se, it's more like the definition of how you would then use multiple vendors, equipment to build a radio network. So I'm going to touch on the distributed RAN. This is, as was kind of pinpointed in the previous presentation as well, the DRAN is the traditional integrated base station with backhaul connection to the first port of aggregation there. Then you go into the centralized RAN, which is basically an architecture in which the base station is split into two parts, the baseband unit and the radio head. Now, continuing on that path, then you have the virtualized RAN, the vRAN or cloud RAN, whatever you want to call it, which is basically an evolution of the centralized RAN, which basically consists of a centralized pool of the baseband units and virtualizing the RAN control functions and service delivery. So with the virtual RAN, the baseband modules is actually moved away from the base station to the data center, which now means that now you start to actually run those functions on computes. So you virtualize everything. So is your network prepared for 5G transport? I'm going to kind of ignore the upper part of this slide where you talk about the different bands. You have the millimeter wave, you have the C bands, things like that. And instead, kind of pinpoint the transport requirements and the technologies. I think the technologies became pretty clear in the previous presentation, but the transport requirements from a capacity, interface, and sync point of view. So looking at capacity, the previous generations actually, as you can see, you had a few hundred megs capacity need for that one. Now with 5G, you actually go into 20 gig or so capacity need. And this goes back to my previous statement saying that, okay, if I'm going to go from purpose-built hardware into running those functions on computes. That's obviously going to put a demand on more capacity. In addition to that, which is pretty clear, is that obviously you need to have, the interfaces on your compute is going to move into like 2 times 10 or even 25 gig on the compute side to be able to cope with those functions running on computes. And then, as we heard, you go into the backhaul and the fronthaul part, moving from CPRI into eCPRI and things like that, and multiple run architectures as previously kind of I alluded to. So this is a pretty busy slide, but if you now look at the upper part of this slide, it clearly shows that you go from a radio head and your baseband unit into virtualizing those in 5G. So you have your virtualized DU and CU, which is, as said, the CU is the control plane of the user plane, the DU is the virtualized, latency sensitive radio functions. So truly looking at the lower part of this, illustration, you see clearly the 4G part, which was touched on in the previous presentation, your backhaul and your fronthaul. Fronthaul being TDM because it's CPRI traffic, while now on the 5G model, you start to look into the midhaul and the backhaul part, which truly have the requirements of dynamic multipoint connectivity compared to the 4G model where you actually had point-to-point connectivity based on layer 2 carrier Ethernet. And then on the fronthaul side, you start to move into a packet-based infrastructure there due to the fact that you have eCPRI running, which we heard is a packet-based technology, as well as the radio or Ethernet there. So that on a kind of high level to set the foundation for this talk going further. So the CRAN part, or the virtualized RAN, or the cloud RAN. Now, I've been kind of alluding to the fact that you start to virtualize things. So if we think back like a couple of years, it would have been pretty unlikely for service providers to actually think about, virtualizing their networks. So 5G came with force, and with 5G came actually new demands for more flexible architectures, as well as designs and deployments, and more scale, as I have kind of been alluding to in my previous slides here. So with that in mind, and when you now start to virtualize those functions, what you actually see in this illustration is a hub and spoke model, where in the spoke you have your radios. So be it a light bulb, radio sitting on a macro site, sitting in any kind of a site. We do understand that with 5G you get into much higher density from a radio point of view. So ignoring for now the fronthaul part, which is packet-based eCPRI, as we learned in the previous presentation, looking at the hub site. In the hub site you now start to see some kind of a data center fabric. And that data center fabric, depending on if you talk about the deep edge, the edge could be of various sizes. It could be a small, 2-node fabric, or it could be, as you can see in the illustration here, a 3-stage claw architecture, spine leaf architecture, running things like BGP on the IP underlay together with EVPN VXLAN on the overlay to connect the computes. As we previously kind of learned that the computes are now going to host your CU and the DU functions running, on kind of generic compute platforms. And now you start to look at actually moving the 5G radio functions into using computes, which is, COTS hardware with some kind of aggregators. In addition to that, you now run those kind of 5G or those RAN functions on microservices running on containers on bare metal servers. You start to utilize, cloud native technologies like Kubernetes for that one, and then, adapt to DevOps principles for that one. And now the key thing is that you also talk about end-to-end lifecycle management here, which is then basically going to be not only for your radio part, but also your transport part, meaning, things like management, orchestration, automation, all those different things, hitting truly the RAN and the transport part of that. So this to kind of build an overall picture of, as I mentioned on my kind of first slide, that 5G is going to be a huge, have a huge difference to the previous generations of the mobile networks in regards to the transport part there. We kind of heard in the previous presentation about this one as well, the cell site gateways, which actually start to move the layer 3 boundary more towards the edge due to the network slicing things and due to the fact that you start to isolate different services based on the service types. So this is more or less a kind of recap of the previous presentation as well. But anyway, I want to kind of mention this. You have different use cases, applications defined for 5G. Hence, you have the network slicing. And you have use cases like the enhanced mobile broadband, which is an SD-WAN-like use case or application where you basically need bandwidth, right? It's not latency sensitive as such. Then you have the URLLC use case, which, using the kind of famous example for that one is the autonomous driving. And that is obviously latency sensitive. So now you start to see traffic that might be within an area or region. Meaning that you basically have now traffic, going within an edge data center. Could be CU to CU communication there. That's why you start to see now, the demand for multi-destination connectivity for 5G. And then you have things like Industry 4.0, IoT, obviously having things like security in mind, QoS, so on and so forth. So clearly you can see that you have different applications, use cases having different demand based on what they are. So kind of picking on the previous use case for URLLC, where you talk about latency. So obviously, as we heard in the previous presentation as well, PTP is kind of one of the key factors that your network do need to support going forward for 5G transport. So just to recap, what is PTP? It's a protocol for distributing precise time and frequency over packet networks, defined in the IEEE standards. The first kind of version was released back in 2002, which targeted the LAN applications. The second version was actually released 2008, which kind of brought the telecom networks into the picture. And there is a third version under discussion, as we kind of heard in the previous presentation as well. So in a nutshell, with PTP, time is carried in event messages. And these event messages are transmitted from the grandmaster clock to the slave clocks. We kind of heard about the PTP, hierarchy in the previous presentation as well. It runs over Ethernet and IP, and you basically have two different flavors of this. You have the IEEE 82.1cm, which is aimed towards, as said, the carrier word, and then you have the 82.1 BA, which is more aimed towards AVB and industrial automation. Obviously, both of these falls under the TSN umbrella defined in the 82.1Q, which basically defines deterministic messaging over Ethernet networks. And we kind of heard about, the telco part here with things like preemption, which allows you to blend the Ethernet traffic and CPRI, eCPRI traffic, We also heard about the radio Ethernet, which is a way of encapsulating the CPRI traffic into Ethernet. So going into the profiles, these profiles were discussed in the previous presentation as well, but I just want to recap these because they are kind of important. So in short, back in 2008, when you basically had the first PTP version defined for the telco world, you also had the first PTP profile defined, which was referred to as the 8265.1, which defined the support for frequency synchronization over the telecom networks. And obviously, it was used for the cell base station synchronization. Now, going forward, as we heard, you have two new profiles. You have the G8275.1, which is the full timing support, and the 8275.2, which is the partial timing support. And as we heard in the previous presentation, there is a main difference between those ones. Now, the 8275.1, the full timing support, do require boundary clock at every node within your network. Each node within your network needs to actually have PTP support supporting boundary clocks. And obviously, the intent with this one is that you reduce the time error accumulation through the network. We heard about it. It's, recommends the use of synchronous Ethernet for synchronizing the boundary clock to a stable frequency. And it operates over layer 2 Ethernet networks and supports multiple active grandmasters for redundancy. The second one, which was touched on as well, is the partial timing support. And the intent of this profile is obviously to be able to support current networks. Not everybody have the luxury of greenfield installs. So you need to support current infrastructure you have in place to be able to actually provide the frequency time and phase synchronization over those networks. So the key features of the partial timing support profile is it operates over existing switches and routers using unicast IP. It uses boundary and transparent clocks where necessary, and then supports multiple active grandmasters for redundancy as the previous 8275.1 profile as well. So to put this into some contexts, I don't think this was went through as such in the previous presentation, but to explain the illustration here, it's quite clear that you need to have some kind of sync between your base station and your grandmaster, and PTP is a mechanism to be able to do that. What you can see in this illustration is basically that you have your grandmaster clock, which is a boundary clock responsible for generating the PTP packet, which is then going to be obviously transported over your network or all the way over to each and every base station or cell site, which means that you basically have a path for each and every base station here through your network. In addition to that one, the grandmaster clock is going to derive its reference sync from a GNS satellite in this example, as we heard in the previous presentation as well. So on a higher level, this is actually how you start to look at this one from a PTP point of view. Now, as we heard in the previous presentation as well, you have the magic number of 3 microseconds. This is the 3GPP defined TAE, stands for the total for the alignment error, which is a relative measurement. So what happens here is the TAE stands for the timing alignment error, which basically means that how it's defined is that you have actually 3 microseconds TAE between any two RUs. So that basically means that between any RU and your timing grandmaster, you basically have the 1.5 microsecond as your TAE defined. Now, to add more complexity to this, you have things like the coordinated multipoint, which obviously goes hand in hand with the fact that 5G is going to have high density of the cell sites installed. So you basically have the same network to provide connectivity for many base stations. So it's fair to say that accurate timing is no longer nice to have, it is truly required. And testing timing is a large new challenge for the CSPs. How would you test things like this? As we are talking about the 3 microseconds and 1.5 microsecond here as the figures. So there is a mechanism in place for that one. So you have a couple of key factors for accurate synchronization. So the factors that make the synchronization poor are actually two. You have the DTE and the CTE. So the DTE stands for the dynamic and the CTE stands for the constant. Now the CTE is the PTP packet latency asymmetry, while the DTE is the PTP packet latency variation. So the illustration you can see there is basically a recap of what we were, where I were making the statement saying that 1.1 microsecond is your total TAE within your network. So how comes 1.1? Due to the fact that you had the 400 nanoseconds, which add in the over air. So from a network point of view, your TAE is 1.1 microseconds. So how is this then kind of dealt with? So I was mentioning when we talk about PTP that you have your event message. So think of the event message being the event message is the packet flow, or the packet timing signaling. And this is obviously then derived from the fact that you start to look at or compare your T1 and T2. So your timestamps T1 and T2, and then basically synchronize accordingly based on those timestamps within your PTP event message. So this is an example of how you actually build this up then. So you have your 1.1 microseconds, which is the network wide, and then you have 1.5, which is from an end station's point of view. So how this builds up is that you introduce your PRTC or your timing grandmaster, which is then going to add some kind of a timing error due to the fact that it's going to place the packet in or place in the time in a packet. Then you go into your network part, which is based on the DTE and the CTE part. The dynamic comes from the random error due to sync Ethernet, for instance. And then your CTE, the constant, is based on your network elements, based on your switches. That, as we heard on the previous presentation, you have different classes. You have class A, B, and C. And those are going to introduce different levels of timing alignment errors. And then you have your link asymmetry delays, which is basically your link latency here. So this is from a network point of view, how you would measure this then. And then as said, you get into your end application noise here to basically have the 1.5 being your total that you have to deal with. So this was kind of a pretty fast walkthrough on transport network requirements. Obviously, didn't touch on all of those. Just more or less wanted to pinpoint a few things that you need to take into consideration when you start to build these transport networks. So on that note, this kind of concludes my presentation. Any questions? Okay, thank you. Do you have any questions?